right, so I hope this looks a little bit familiar. I asked you to look at section 5.2 in your textbook where there is a similar animation there. There's lots of details. We'll get to all the details on that. But looking at this animation of our rocket-powered basketball, because there's a lot of those, dangerous, watch out for them. There's a function on the left that's graphed. You can't necessarily tell from this picture what's going on from your distance. I can read it on mine. You might remember from reading in the textbook last night, but what kind of function is this v? We have y equals v of t graphed. Is it a rate of change function or is it an accumulation function? It's a rate of change function. And it's not by looking at the shape of it that you would know that. Take a look at either in your text if you can see this, or the units on the y-axis, or if there's a description somewhere when you're looking at graphs. This one, it's really small on there. You might be able to see it if you're in the first few rows, but you should have seen this in your reading last night. It says, the vertical says velocity in meters per second. So meters per second sounds like a rate of change of, well, something with respect to time. So we've got meters measuring, in this case, the height that the rocket basketball is gaining with respect to time. So we don't really know exactly where it started. In this picture, the way it's drawn here, it looks like, well, maybe it's got a little ledge that it's starting from. We launched it from something. But just tracking what its velocity is, measured in meters per second, is tracking its rate of change. So this velocity goes up and the basketball goes up, but those aren't showing the same thing. This isn't a picture of what the basketball is doing. So don't get confused by, like, there's another picture over there, it's going up. Oh, this just means the height is increasing. Well, the height is increasing, but what we've got on the left here is something that shows what its rate of change is. So the rate of change starts at 0, 0. So at time 0, it's not moving upward at any number of meters per second. It's stationary. But as soon as a little bit of time has elapsed, we have a velocity that's non-zero. What happens to the velocity, the speed at which this ball is rising as time goes on? It increases. Is it rising at a constant rate the whole time? If I look at all 8 or 10 seconds that I can see in this? No. Velocity clearly goes from 0 up to something that isn't 0. So I don't have a constant rate. I have a rate that starts small and gets faster and faster, kind of like the reverse of the oil spill. The oil spill, we started at a high rate of oil leaking in cubic meters per day, and it decreased quickly to being lower, not to 0, but went from things around 30 to down close to 3 cubic meters per day. So it wasn't constant, but that doesn't mean that we can't still utilize our constant rate of change functions as long as we do it carefully, as long as we look at only small moments at a time. So this v is a rate of change function. The dependent variable shows us the rate, shows us the speed at which the ball is rising. So our goal for today, and probably finishing up some notation stuff at the end of Friday that's a little bit more complex, beyond what we've done before, is to do again what we did with the oil spill, but I hope at this point it seems kind of familiar what our process is going to be, so we'll step through it maybe a little bit more quickly at first, but then take more time at the end to talk about how I create a function that models the height of this, accumulated height since it began, regardless of necessarily how high it started. How high it started is just the difference between, if you remember that bathtub graph, did it start at 0 or did it start at 2? I don't know, but after that it was at 1 rate of change. That was easy because it was 1 constant rate of change all the time. But total height of the basketball versus how much height it's gained in this case, since I know we've got positive rates, meaning it's going up. The only difference between those is starting point. If I'm measuring the accumulated height just since time 0, the height that's accumulated at that point is nothing because we haven't started moving yet. So we start from nothing if we're measuring just this net accumulation since the beginning, whatever this beginning is that we're concerned about. And then starting from zero and in this case going upward because we've got positive rates that we're using indicating more meters above the ground. So with this velocity function, just make sure whenever you're looking at a graph, because we've probably most of the time when you look at graphs, you think of them as the vertical is how much of something there is, like the accumulation sort of function, but this is a rate function. This is the how fast is something moving or how fast is something changing or at what rate relative to something else is one quantity changing. So make sure you always look at the units to be sure you're interpreting correctly. So think carefully about graphs. Don't just jump to conclusions about what it is, like, oh, it goes up, so this is the basketball going up. It's from, if you had never seen the examples in the book, and if you're sitting in the back right now, I can understand that, because this looks like, oh, there's a ball going up, and there's a graph going up. Therefore, this is modeling the height over time. But it's not. Even with the letter, if it was h of t, that would be sneaky of me if I said, oh, h of t, ha, 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 that's not really the height, that's its speed. You have to look at the units really closely. I'm not going to try to trick you, but just if it's something generic like F or G, make sure you're always looking for what are the units on the quantities that are being compared in the graph instead of just guessing or assuming what it is that it's showing. So in this velocity function then, talked about, the independent variable, the quantity that's on the horizontal axis, the independent variable is apparently t, and it's representing time in seconds since the ball was launched, or since we started caring about it, but let's say time in seconds since the launch. And then the dependent variable is the rate of change of the height of the rocket, measured in meters per second. The dependent variable is just called y here. We have a function v that relates them. But the meaning of it, what's being measured as the dependent quantity, is this rate of change of the height with respect to time. All right, so how could I express exactly, not making an estimate based on what it looks like from a distance, but just how could I say exactly the coordinates of the point, the correspondence pair of the point in this graph when t equals 5? So first part would be 5. What could I say about the second part? What would the corresponding part be if I want to state it exactly somehow? Yeah. Yeah, 5 comma v of 5. So 5 for the independent part, comma, I could maybe make a numerical guess about this, but v of 5 would say it precisely. Let me pause this and scoot this over to, here's a spot right here where I think I have this lined up so the independent value is approximately 5. Dependent value looks like 7 or 8 or something. Don't go by that. If you had a formula for v of t, we could substitute in and get, maybe it'd be a nice value, maybe it'd be a decimal approximation, but we can always just say, as long as I have a function name for this, even without a function rule, I have this function notation set up so I can say 5 comma v of 5. And that should directly, exactly, be able to discuss that point there. And v of 5, what would this mean? Yeah.
It's the rate of change at that time.
It's the rate of change at that time. So at 5 seconds, the height is, I can see from the graph, it's increasing without estimating that it's increasing. It's definitely increasing at a rate of v of 5 meters per second, whatever that is. V of 5 seems to be like 8 or 9 or something, but this is a speed or a speed at which the height is increasing, or a rate of change of the height, v of 5. All right, so if I wanted to talk about how to use this v of 5, we can only use rates of change, as you talked about in recitations and blurry pictures and all that sort of thing, and we talked about in here before. You can only use a rate of change if you have something changing. So if I say time stops at time 5, there's nothing but time 5, how fast am I going? That doesn't really make any sense. We have to have a little bit of an area around a small moment around t equals 5 in order to be able to think about how this change is being used. But if I only stick to a small moment around time 5, then we can use our constant rate of change mechanisms to play around with this. Say, oh, this is how this rate is useful. Because I could say, well, if this is meters per second, like 8 or 9 meters per second, if you were thinking like low-level rate of change thoughts, like, okay, so in the next second I go 8 or 9 meters up. Well, probably not, because I can see that this rate's changing all the time. So instead of doing that 1 meter at a time or 1 second at a time sort of interpretation of this, our more general interpretation, if I have this rate that applies in the moment where t equals 5, what can I say because of that rate? In the moment t equals 5, let's see, for any small variation in time, if I go forward a little bit in time, if you want to specify, if a little bit more time has elapsed, then the height will have changed by v of 5 times that much, right? dy equals mdx, the change in the vertical aspect of the ball is going to be v of 5 times as much as the little tiny increment of time that we allow to pass, or that we imagine going by in the small moment around t equals 5. So if I think going from time 5 to 5.001 seconds, then I could calculate, well, I could express then 0.001 times v of 5 would be how much the height changes. And if I guess that it's like 8 or 9, then I could say, okay, so 0.008 or 9 would be how much the height changes measured in meters, right? So the whole purpose of the constant rate of change isn't so that we can be done with it when we're not talking about linear functions anymore. The point of constant rate of change is that we can use it in all of these situations if we think about things like this, where we do actually have a varying rate, but think of just small moments at a time where it's essentially constant. So the variation in the height of the rocket, if I'm looking just in a small moment so that I can use these differentials, these small changes in the variables that we treat as essentially, we use them if we're talking about a constant rate of change, like the dy and dt here. But if I let t vary by just a little bit, dt, then y, the height, will vary by just a little bit also. It'll be, well, v of 5 times as much. I don't know how large v of 5 is exactly, but it's not infinitely large. So variation in height of the rocket is v of 5 times this corresponding small amount of variation in elapsed time measured in seconds. So dy equals mdx, just switch the letters. We have a specific value of m that we're representing, v of 5, and instead of dx, we were told that the independent variable we were using was t. So switch this out, but it's still our same key piece here. Rate of change, when we're using a constant rate of change, we have this relationship all the time. A small variation in one variable is going to indicate a multiple of that small amount of change in its related variable. So, all right. Let's say we want to estimate height then, like what we did with the oil spill. Estimate how much oil had been spilled. Estimate how much height the ball has gained since time 0, regardless of what its overall height is, how much it's gained since time 0, where this graph begins. So as a project, I'm going to pause this when it gets to there, something later. So let me pass out something to you. This already has this on there. So we're gonna, what we did last time with the oil spill, I'm going to pass out a piece of paper in just a minute. So if I want to estimate, I need some specific expressions that I'm going to use. I need to set up how I'm going to do this estimation. With the oil spill, we chose every 0.3 days, and we picked a rate to use for a little while. So again, so that this is manageable, as opposed to like, oh, there's infinitely many rates. Let's say every 0.9, to pick something that will be easy to distinguish from something else, every 0.9 seconds. So I've got 0, 0, or 0 comma v of 0. It is obviously 0. And then 0.9 comma v of 0.9, 1.8 comma v of 1.8, and so forth. So let's see, 2.7, 3.6, 4.5, and so forth. So if these were every 0.9 units along the x-axis, then that indicates what we're doing with this is we're just regulating how we're going to do this. Instead of picking points just kind of randomly every so often, say, you know what, I would like to estimate how this height's changing. So I'm going to use constant rates. There's infinitely many rates shown here, so I'm going to pick some of them. I'm going to just pick every 0.9 units, I'm going to pick the rate on here. 0.9 chosen arbitrarily, just because I said so. There's no rule about 0.9 or 0.3 or anything in specific. Just choosing smallish numbers. These are closer together than the 0.3 days we were using yesterday. But our goal was, all right, so I'm going to use this rate for a little bit. Or in other words, what I'm doing is I'm pretending that my rate function looks like a constant going straight across. We said constant rate functions look like horizontal lines. So that bathtub rate was 2 gallons per minute, or whatever number it was, 1.5 gallons per minute all the time. Horizontal line segment or horizontal line would indicate if it's a rate of change graph, we've got one constant rate. So I'm going to use one constant rate for a little bit, then change to another constant rate and use that for a little bit. I'm pretending my rate function looks like this. Now it doesn't in reality. I'm picking a point on the curve every 0.9 units and using it for a while. 0.9 units, start at the value on the left, open up to on the end. So between, for instance, 0 and 0.9 in the sense that I'm going to include 0 and then not include 0.9 for this first segment, and so forth. You can't have a rate function that has two different values at 0.9, so I'll use the one that's on the curve every 0.9 and then extend and do the kind of open endpoint. But you won't see open circles, that just kind of makes a mess of it. In any case, so I'm just pretending my rate function looks like this. And the reason for that is these are reasonably small moments. They don't do a great job of approximating this curve, but it's actually pretty good when we come down to it, when we come to looking at, well, how much better would this get if I made these shorter? It doesn't actually get a whole lot better, surprisingly. But what this means is, oh, for the first 0.9 seconds, I know that that rate is 0, so I don't have to say it's v of 0, but it is v of 0. So this rate, r, no, not r, well, in our other notations we had r sub something, but our rate at this point is 0. It's also v of 0. The other ones, we'd need to have a function rule in order to determine what they are, but that one clearly is at the origin. So I'm going to use the rate of 0 for the first 0.9 seconds, which means in my approximation, it's going to be a poor approximation for those first 9/10 of a second, because in my approximation, rate of 0, that would mean the height is not changing. So nothing happens for the first 0.9 seconds, when in reality, I know during that 9/10 of a second, there is some height being gained at varying rates that aren't 0. But we'll go on and pick another rate after 9/10 of a second have gone on, and then we'll have a positive rate of change, and so forth and so forth. So here, let me pass this out to you. It's got the horizontal line segments drawn on it already. Oh, here. So one side says task 1, and the other side says task 2. We're going to start with task 1, just to be organized about this. Thank you. That's not what I was trying to click on. There we go. So again, the first step, our overall goal, and we'll get back to the steps. Overall goal is I have an exact rate of change function. If I want to figure out what happens because of that, I can't actually, in my brain, computer can do this, kind of. I can't use all infinitely many points, rate values, and get this done in a finite amount of time. So a computer can use like 1 billion points and then take it, half a second. So we're going to use like 4 or 5 or 6 points and take a half hour to do this. But the process is, just as an example of what's actually going on, and this is actually kind of what's going on inside computers that are computing these sorts of things. They aren't like solving equations and remembering formulas and stuff like that. They've got a process of approximations. It's all numerical computation. So if I have something like this that has infinitely many different rate values, and I want to figure out what happens because of that rate, I'm going to choose some of them. And so to set up a problem, as computers have a certain number of calculations built in that they're going to do, we're going to say, okay, we're going to calculate this by using a rate every 0.9 seconds. Again, if you were doing this yourself without guidance, you could pick whatever number you wanted, but let's all do the same number, so let's pick 0.9 seconds. Every 0.9 seconds, 9/10 of a second, we're going to use a value of, or an expression for the value of the rate, and use that for a period of 0.9 seconds. And what happens because of that, using it as a constant rate for that small interval. So every 9/10 of a second, we're making then moments where we're pretending that we've got a constant rate over that moment of 9/10 of a second. And we're going to call this delta t. T is our independent variable. dt represents a variable that's within a moment, a small amount of change in t. I'm saying that delta t equals 0.9, and 0.9 is how wide these intervals are going to be. Does that make delta t a variable or a parameter? Yeah, it's a parameter. It's something that we're using for this problem today. If you're going to do it on your own, you could pick a different number for it, but delta t doesn't change. I don't get to pick other numbers for it in the middle of doing this. This is just a parameter. It's not the same as dt. dt is a variable that varies within our moment. This delta t is the size of our moment that we've chosen, just to be regulated about this in advance. Instead of picking a moment based on what the graph looks like, we'll just say, let's just pick a 0.9 and see what happens. So this delta t is a parameter, and let me move this out of the way. It'll allow me to. So what we want to do is sketch an approximate rate of change function. We can call it r, we can call it, well, we've called them all r before. In the one we talked about the other day, we had r sub v for the rate of change of the volume, and then our approximate was just plain old r. Here, our velocity was just called v, not the same sort of notation, but we'll still call our approximate rate of change function r, just approximate rate of change. That way we know what we're talking about, just same sort of plain r as we talked about the other day. And we're going to do this like I just had a sketch up there a minute ago. Every 0.9 units of t, we're going to select a value on the curve and use that for the next 0.9 units. So, meaning, if you can imagine, as time goes on, generating this approximate function graph, we'd be like, instead of going up on a nice curve, we'd be doing these little steps. It's called a step function, these sorts of piecewise constant functions. Go across, go across, go across, and then just jump from step to step to step. So these are the function types I want to make when I'm making an approximate rate function, because I know how to use constant rates. I know dy equals mdx. That's a good tool to use. We can figure out what accumulation happens within each and every full interval or during any part of one of these little steps here, because we have one constant rate that we're going to use instead of the curve that has a lot more different rates to it. So we're just going to pretend the curve doesn't exist and just use these steps as our rates instead, which doesn't look extremely accurate, but it's okay. So here's what you have on your paper. It says task 1, find the approximate height of the rocket by t equals 5 seconds by using moments of delta t equals 0.9. All right, so this is kind of the slightly more advanced version of You drove at 45 miles an hour for half an hour, and then you drove for 50 miles an hour for half an hour. Where were you after 45 minutes? You know how fast you're driving all those times. If there were constant rates, you can do that rate times the amount of time that passed at that rate, multiply them together to get the change in position on the road. In that case, this is just basketball question. So same sort of thing. I've got a rate that I don't, well, we have a formula for it now, t to the 1.3. But instead of doing a numerical computation, let's just first think about the symbols for this. How would I find the height of the rocket by time 5? T equals 5 seconds. And then we can think about how we can write that in terms of symbols. And we can go back and do some numeric computations and figure this out also with our approximation. So this isn't going to be exact. It's going to be approximate because we're not going to use the exact rate function at every point. We're going to use the exact rate function at some points and use approximations, use that as an approximation for the next small moment. So how many different, if we're using our approximate rate function, how many different speeds, velocities, are we going to end up using in order to compute the distance that the ball went upward between time 0 and time 5? How many different rates apply between there? How many different of these delta t intervals would we go through? 0 to 0.9 seconds, we would have traveled that whole 0.9 seconds. Yeah, so we're traveling at this lowest speed. Let me get my pen back on here. So yeah, we'd use this speed for the first 0.9. This is up to 1.8, up to 2.7, up to 3.6, up to 4.5, and then a little bit, not all the way through that last interval there, but partially using this speed that starts at 4.5 and would go all the way up to 5.4, but we're just not. But this is, I'm traveling at this speed, or the ball is going upward at this speed, speed 0, for the first bit, the next speed for a little bit, the next speed, the next speed, the next speed, and then this one for a different amount of time. Because it doesn't, by time 5, we haven't used all of what the distance that we'd use that rate for. We could use that rate all the way up to 5.4. Well, up to, not including, 5.4, but in that last 0.000000001 second, I don't think you're going to get any farther, really. So if I want to find this expression here, think about this for a minute. Write down in symbols, well, for the first unit, for this first interval, for instance, I know that's 0, or v of 0, as my rate. If I use that rate for a full 0.9 seconds, I'm going to have 0 times 0.9 mdx as my distance upward. Now it's going to be 0. Write that up for the next, symbolically, for all of the units up here that we need, including this last one, which is going to be formatted a little bit differently, but the rest of them are all kind of similar. So you've got a space to write this. It'll be kind of similar expressions over and over and over for how much height is gained, since it is positive rates, how much height is gained during each of those intervals. If you want to be like all symbols, v of 0 times delta t. So again, we're pretending the ball is moving upward at one rate for 9/10 of a second, then another rate for the next 9/10 of a second, then a third rate for the next 9/10 of a second. Which it's really changing speeds all the time, but for this purpose of we're not computers, I don't want to change this every 0.0001 of a second and try to figure out something. We'll do a rough approximation, but it's really not actually that bad. So we have 1, 2, 3, 4, 5 complete or completed delta t intervals, ones that our time is all the way through by the time we're at t equals 5. And then we've got one that t is in the middle of. That's the distinction between these complete and current intervals. But, let me clear off. So I've got a little part here. How far into this current interval is t? Yeah, it's just between, this ends at 4.5 and I go up to 5. So 0.5 seconds at that longest rate. So it's just wherever t is minus the beginning of the interval. So if t is at 5, t minus beginning of the interval, which is 4.5, tells us how far we are into that. So symbolically speaking, in the complete intervals, and I just wrote out the pseudo-numeric versions of these, our velocity times delta t each time. So v of 0 times delta t, v of 0.9 times delta t, v of 1.8 times delta t, and so forth and so forth. So it's this repetitive pattern, same sort of thing, over and over and over again. There's probably a shorter way to write this. The expression down below with the numbers actually using this formula and also putting in the delta t's, we still got, even putting in the specific formula, I've got 0 times 0.9, 0.9 to the 1.3 times 0.9, 1.8 to the 1.3 times. Why isn't this 1.8 here in this third term? It says 1.8 to the 1.3. Why isn't it times 1.8? Yeah, this 0.9 isn't the t value. This 0.9 is the delta t value. So this 1.8 is substituting in, so we've got v of 1.8 is 1.8 to the 1.3, because v of 1.8, or v of t, is t to the 1.3. But this 0.9 that shows up in every single term, that's that delta t. That's the width of the interval, that parameter that we set up at the beginning of the problem. So if you can see what's going on with these, we've got our velocity function evaluated every 0.9 units. So it's evaluated at different t values. But each one of those is multiplied by 0.9, the length of this interval, this parameter that we set up. So the numbers inside the velocity function and the delta t's outside, those are related. The ones inside are multiples of delta t. The ones outside are delta t. All right, now in this current interval, slightly different, because we're not using this last rate for a full 0.9 units. We're only using it as far as we are into that interval, which is half a unit, as we decided, 0.5 seconds. So you could think of it as dt, or since t varies within the interval. Another way to think of this that maybe is more clear, what we were talking about earlier, this part here, it's just, well, I found this 0.5 by doing t minus the beginning of the interval, which was 4.5. So this dt was t minus 4.5, or in general, numerically speaking, it's 5 minus 4.5, using the specific numbers of the problem instead of symbolically. 4.5 is not a symbol, but we'll get into how do I describe in general the beginning of an interval. Well, we'll get to that. That's some of the symbols we're going to work out end of Friday and all of next week. But you can see that there's a lot of repetition here in how you write this out. Now, what if I needed to do this? What if I split this into intervals of 0.001, like a computer might do, or 0.00001? You could write out the symbolic version in a long time, but once you get the pattern, you're like, all right, it's the same thing over and over. How can I write this more succinctly? That's what we're going to be working on next. Our goal is to, I don't know why this is frozen. Our goal is going to be to use sum notation. Those of you that have recitation already on Friday or Monday have already talked about sums in recitation. We'd like to be able to express this, adding up a whole bunch of stuff that's almost the same and just changes at a nice regular pattern by writing the sigma notation, telling us how many terms we're going to add up that are all basically the same term. So if I wanted to express, let me just do this on here, for instance. If I just want to express this first bunch of things here, our sigma notation says, well, we're going to take this and say, well, what are all of these terms like? They're all velocity evaluated somewhere or another, and they're all exactly the same in terms of they're all multiplied by delta t. And so using summation notation, this says add up a bunch of things that are of this form. Now we'd have to write in an expression here, and that's a little trickier. And that's what we're going to focus on Friday. But we're adding up a bunch of these. How many do we add up? So there are things that we do with sums. If you haven't seen these before, it's called using an index. I want to add up 5 of these things. So I'm going to use an index that appears in this, how I describe what it is that I'm subbing in here. I'm going to use the letter J. I'm going to substitute in J equals 1 through 5 into this somehow and make it come out to be all of these numbers. So that's a little bit, we have to kind of create a linear function to put in there. We'll work on that. That's coming up next. But there's a mystery thing that has to be in here in order for me to be able to substitute in the numbers 1 through 5 to get these 5 different terms. So the stuff inside is that's Friday's task. But prior to Friday, this thing is frozen right now. I don't know why this isn't. Hold on. There we go. Sorry, it just froze on me. So prior to Friday, think about writing approximate rate functions, task 2. We did this a little bit with the oil spill. The rate function part's not too bad to write. The accumulation function part is kind of a pain. That sum gives us a different way to write that accumulation. The one that I just started to write, where I wanted to add up the first 5 terms, that's for one specific value of t, how much height had accumulated. So if I want to do it in general, I just have to figure out how do I express in general how many intervals are there going to be, and then we can write it as a sum instead of the accumulation, which I don't even have that up there yet, the accumulation that we saw one of them for the oil spill, and they're kind of a mess. But this rate function is not too bad. Piecewise, it's a constant, right? So for the first interval, for instance, we said that the rate was v of 0, which we also know happens to be 0 from the picture. But that rate applies if t is between 0 and 0.9. And we'll do the less than or equal to's and less than's this way so that there's a big dot on the curve and then it extends out to the right. We jump up to put our next dot down. So at the right end, you can imagine there's like open circle if you want to, but that just kind of makes it look messy. So standardly speaking, graphing calculators, graphing programs don't put dots and circles. That's for like teachers to be able to grade your work. You generally read through the notation to see where the ends apply and where the value is. So this explains the dots and circles part. All right, so what's the next value of the rate I use past this one? I'd use the rate evaluated at 0.9 if t is between 0.9 and, 1.8. So you can numerically estimate these, but this is how we're going to do these approximate rate graphs. I'll call this a left side approach, meaning pick a rate and then use it for a little while afterwards. So there's a dot at the left side, or these constant steps are attached by their left end of the step to the actual rate function. So if you see this left side approach, that's the way we've been doing this. Pick a value and use it for a little while. Then go back to the curve and use that new rate for a little while. So finish up this rate function. Shouldn't take too long. Then we'll take a look at the accumulation. There is. Yeah. So I put this up in interval notation just to save a little bit of space. Keep in mind, if you do see interval notation, GC doesn't do interval notation because it uses parentheses and brackets for other things. But if you do see interval notation, remember the square brackets means the included, the or equal to sort of inequality, and the parentheses mean the excluded variety. But your rate function would look something like this, right? So because of our parameter that we set up of delta t equals 0.9, we reevaluate every 0.9 units. So our approximate rate function is based on the exact rate function at a few different points. I mean, there's infinitely many if we wanted to keep continuing, but discrete set points, we could count them, how many we're going to be using. For any value of time, how many would be needed. There's going to be a specific number that I can count and figure out how many different rates I'd be using. So just keep in mind, when we're writing this accumulation function, our goal isn't just to find coordinate points for the endpoints of these. Our goal is, well, if I have a t value that's between 0 and 0.9, how would I describe the accumulation? Not just where's the endpoint of that section, but how do I write the equation for that line segment? So equation of a line that just has a domain restriction on it, between 0 and 0.9. Well, that's the boring one, because what's the rate? The rate's 0, v of 0. But in general, if I want to write an equation for a line segment or a full line, I need a starting point and a direction to go. So in terms of things we've talked about, y initial and mdx, a slope and how far I change. So for the first unit, I know my slope, my rate of change is 0, that v of 0 is 0. But if we think about this starting point, oh, we're starting from 0 in the first unit. So the accumulation function starts out nicely, starting from 0 and changing at a rate of 0. Well, we're going to still be at 0 by the end, but the equation for that, in general, I could write this. Now there's r of t here, and we did this last time too. R of t, if t is between 0 and 0.9, well, here's r of t. Oh, it's v of 0. So this is just to shorten up what we're writing here. I can write r of t when I'm talking about t in a specific interval, the rate that we've changed by. So this red expression here is the rate that we use everywhere between 0 and 0.9, and t minus 0, instead of just saying times delta t. Because not every point is 0.9 units away from this. That's where I am by the end. If I'm trying to figure out an endpoint here, I'd be at delta t comma 0. But I want to describe that line segment. So I need a y initial plus mdx. Well, when I'm between 0 and 0.9, how do I find that dx? It's dt in this case. Oh, I compared how far I am past the beginning of the interval. Remember that what's the end part of that when we're at t equals 5? We found that 0.5. This t minus 0 finds the equivalent. How far am I into the interval? For any value of t, not just when I'm at the endpoint of 0.9. Well, not even really supposed to use that endpoint there. But when I restart my second interval, so my first interval, what I've drawn is the function as it increases from the origin to 0.9 comma 0. The next interval, I need to write the equation for this line segment that extends from that point, 0.9 comma 0. Here's my starting point, and increasing at a rate given by, well, v of 0.9. When I'm between 0.9 and 1.8, I can just use r of t, because r of t is v of 0.9 for those variables. But my dt, if t is between 0.9 and 1.8, like if I asked you, find the accumulation by time 1.2, you'd be using a 0.3 in there, because 1.2 compared to the beginning of the interval, that's how far into the interval we are. So this t minus 0.9 does that computation. Oh, how far am I into this interval? So it's the current value of t, the letter t, minus the beginning of the interval. So that dx expression here, in general, generic letters dx, this tells me how far I am into my current interval when we're doing this multiple interval expression sort of setup. So these start to all look the same also, but this R of 0 times 0.9, this is that completed interval. I went all the way through the first interval. It's just a boring one because we got 0. And then add on what's happening while I'm in the second interval. While I'm using a new rate, current rate, for a little bit, how far? Depends on how far I am into this second interval. But after that, if I'm in the third interval, I know I've got 2 full intervals worth of completed accumulation, height gained, and then what's happening in the third interval. So the stuff in blue is what already happened in previous intervals whose speeds we're done with. And then the last part, the new part, is what's happening during the current interval, the one that the t values are in the middle of. So if t is between 1.8 and 2.7, then I know I have 2 full intervals worth of stuff that is already done, completed, whatever the rate is, times 0.9. Do that twice. That's the stuff in blue. But what's happening in my current interval depends on specifically which value of t I'm talking about. In general, for any value of t in this third interval, this is the accumulation just within that third interval, the current rate that we're using times how far I am into the third interval, how far I am past 1.8. So this is the m dx for the interval we're in the middle of. These are the m times delta x, I guess you could say, intervals we're done with. We're already past those if t is between 1.8 and 2.7. These are already fixed. Nothing else is changing about those. But this part is still going onward. So one more, just for good measure. If I were to go into the fourth interval, I'd have 3 complete intervals that are done all the way rate used for the full 0.9 units, plus what's happening in the fourth interval as we're going through it. We're using the rate that goes with the fourth interval, v of 2.7, and then how far am I past 2.7? That tells me how much accumulation I'm at. If I'm between those two, if I'm within an interval, I need to figure out how much of the interval I've passed so far. If I'm done with an interval, I've used the whole thing. It's 0.9 in this case. Different number in other examples, but the parameter we chose was 0.9. So if you're past an interval, you use the rate for the full 0.9. If you're in the middle of the interval, there's a variable expression describing how long you've used the rate for. You could plug in particular values of t and find values of that variable expression, or how long you're using this rate for, or how much accumulation there is in the current interval. But again, here's our pattern. We've got these 2 kind of halves to the problem here, where we've got the stuff that already happened and we're past, we're done with. How many full intervals do I have and how much accumulation happened there? And then there's one other tagged on part, because whatever t is, it's going to be in the middle of some interval. Maybe we're lucky enough it's at exactly one of these kind of endpoints. That actually makes it a little bit more confusing. It's like, how do I have a moment if I'm between 2 points? But I'm going to be in between, or in the middle of one interval or another. And so my rate still follows the same patterns as before. I could write, instead of r of t in each of these, I could have written v of 0, v of 0.9, v of 1.8, and so forth. So we can still do that. But the other part to this, the dx, it's not 0.9 every time. It's a variable expression that depends on which t we have from within that interval. There's a whole interval worth of t values that apply to each of these. That's why they have the variable t in them still. All right, so in any case, so there's a lot of similarity to how these terms are set up. So what we're going to work on Friday after our quiz is how to use sum notation to write this stuff more succinctly. But we are having a quiz on Friday. It's not going to be a take-home quiz. We're going to do it in here. But it will be about understanding rate graphs. I'm not going to make you write a whole accumulation function or anything like that, but understanding rate graphs, what you can interpret from them, maybe how much accumulation with some specific numbers, that sort of thing. So make sure, I'm going to post some practice, like sort of questions on this, so you have some more things to look at besides the oil spill and the rocket ball. But I will see you on Friday.